welcome to the full version of my talk on private simplification and decoupling without smoothing. So the first order of business will be to define these terms in my title. So first of all, what is private simplification? Most of you have probably heard of it. So here's the setup. So we have a bipartite quantum state here. So it's a CQ state. So we have an A system here that is classical and an E system here that is quantum. And you can think of it as the output of, let's say, a QKD protocol, where the classical system here would be Alice's raw key, and the E system here would be Eve's side information that she managed to acquire during the protocol. And then the private simplification step aims to turn Alice's raw key here into the final key by means of a hash function. So what we want to do is select a hash function at random from a suitable family of hash functions, apply it to A, and then we get a C here, which is going to be the final key. And if it is to be secure, the goal is to have something that is uniform and independent from whatever Eve has here. So more precisely, we want the trace distance between the output of the protocol, so the state we get after applying the hash function, and the ideal key here, independent of Eve's system, to be small here. And what do I mean by small? Well, it's going to depend on two parameters. So first of all, it's going to depend on how much randomness there is in A given E here. So there has to be some measure of randomness that's going to come in here. And it depends on how much key we hope to extract out of it. So the size of the output of the hash function here is going to play a role. Right? So what we want here is to have something like 2 to the, and then we'll have order of, let's say, the number of qubits in C here. So the log of the dimension of C minus, and here we're going to have some sort of randomness measure for A given E here. And I'll get into this very soon. And one important special case here is when rho has an IID structure. So when A is actually A1 to N, and E is actually E1 to N, and it's actually N copies of the same state. So many QKD protocols or other protocols of interest can be reduced to that special case here. So in particular, we want a private simplification theorem to work well in the IID case. Otherwise, there's no hope for it to be really optimal. Now, decoupling is basically the same task in a sense, except that rho AE is fully quantum, which means that here, instead of choosing a hash function at random, we're going to choose a unitary at random from a suitable set of unitaries. And then we basically want the same thing out. So we want the output here to be independent from the Eve side information here. And again, small is going to depend on the same two parameters. And this is interesting in particular in quantum Shannon theory, because it can actually be used to prove a wide range of achievability results via Ullmann's theorem, which says basically that if we can show that, let's say, the output of, let's say, the environment of some channel is completely decoupled from the purification of a state of interest, then we can turn this around and say that the actual receiver has a good decoder and is able to recover what they're supposed to recover, but I won't get into this here. Okay, so I said 2 slides ago that we need some sort of measure of information or of uncertainty about in the state rho AE. So we need to measure how much uncertainty there is in A given E. Here. So how can we measure this? Well, there are many choices available. The first choice we might think of is the von Neumann entropy, which is defined like this here. It has all kinds of nice properties, so it has chain rules. Whenever we have an IID state, we know it's the right quantity to look at. However, in the general case, when we don't have an IID structure, it's too good to be true. Basically, like we're not going to have a theorem that looks like this here, where this here is the Shannon entropy, or von Neumann entropy rather. So in the general case, we're going to have to look at other measures of information. one choice that turns out to work quite well is called the min entropy, which is defined via a guessing game. So it's defined via the probability of guessing E by measuring the E system. This has also all kinds of nice properties. In particular, it can be expressed as a semi-definite program. It's quite well understood. It doesn't have chain rules we do have inequalities, but it's not nearly as good as for the von Neumann entropy. In the IID case, basically this definition by itself doesn't really work. Like we don't get something anywhere close to what we should get, which we know is the von Neumann entropy. And what we need to do for it to be useful in most cases is called smoothing, and I'll get into this very soon. Now, the definition we're actually going to use in this talk is something that's been defined a bit more recently, called the sandwiched Renyi entropy. It's defined like this here. I won't get into the details of this. What you need to know about it is that it's a measure of entropy that generalizes these two cases via a parameter called alpha here. So we have a parameter alpha that's between 1/2 and infinity, and at alpha equals 1 we get the von Neumann entropy. At alpha equals infinity we get the min entropy, and if alpha is between those two, we get some sort of interpolation between these two cases. So it's been recently defined. We're starting to understand it better, and we'll see how it's actually very useful to analyze private simplification and decoupling. Now I'd like to say what we're actually able to do here in private simplification. So here's the main theorem, let's say, in private simplification that is known. So this is from Renner back in 2005. So suppose that we draw our hash function from a two-universal family of hash functions. Then the expected value of so the trace distance between the real output of the protocol and the ideal case here is upper bounded by this quantity here. So we have the size of the output here, so the number of bits coming out of the hash function, and h2 here, and this is the sandwiched entropy of order alpha equals 2 here. So it's somewhere between the 1 and infinity case. So this by itself is not so good for IID, for the IID case, because we know that in general H2 is less than the von Neumann entropy, and we know that in the IID case we should get the von Neumann entropy. So we need to do something about it, and what we do is called smoothing to deal with this. So the first step is that instead of using the 2 entropy, we just go for the min entropy directly, because it's better understood, and it's a lower bound on the 2 entropy, and we look at the epsilon smooth min entropy. And so the epsilon smooth min entropy is that we, instead of computing the min entropy directly on the state that we have, we're going to take the best state that is close to the state that we have. So we look at a ball around, so let's say we have rho here, we're going to look at a ball of radius epsilon around it and take the state in there that has the best min entropies here, meaning the highest min entropy in here. And that's going to be the epsilon smooth min entropy of rho here. And the distance measure here is called the purified distance, but it's not so important for this talk. So if we plug this into to Renner's theorem, we get something like this here. So we get that the upper bound on the quantity we want here is going to be so the same quantity we had before, but with the smooth min entropy here. And of course we have to pay for the smoothing process here by having an extra term here that comes from the triangle inequality. And this works pretty well for the IID for IID states, because we have something called the fully quantum asymptotic equipartition property. So suppose that we have a state rho that is IID here, and we compute the smooth min entropy on that state. It turns out to be at least n times the von Neumann entropy of one copy here, which is what we want, minus a term here that scales as O of square root of n here. So that's a term that we can live with. And I'll go into the core of the proof of this here because it's actually important for the result I'm going to talk about today. And it goes like this. So if we look at the epsilon smooth mid entropy of A1 to n given E1 to n, we first upper bound it by the alpha Rényi entropy here. And for this we actually pay we have to pay a price here of this form here. Now the alpha Rényi entropy here has this property that if we take the alpha entropy of an IID state, it's actually n times the alpha entropy of that state. So this is just an equality. And then we convert this alpha entropy to the von Neumann entropy, because this is what we want in the end. And then we have another term here that we pay. And then to get the result, well, we have to choose an alpha that works. And it turns out that choosing an alpha that's just a little bit above 1, so it's 1 plus something that scales as order of square root of 1 over n, here yields the theorem. For those who are interested in device-independent QKD proofs or device-independent protocols in general, the entropy accumulation theorem works basically in a similar way. So it has the same core of the proof here, except it's a bit more complicated. Now, so what we'd like to do here is to cut out the middleman, so to speak, right? Like, so now we're trying to bound this here, so the smooth mid entropy, to be able to plug it into the private simplification theorem. What if instead of doing this, we could just plug in the alpha entropy directly into the private simplification theorem? So what if instead of having something like this here, we didn't have this epsilon term, and we only had a term here that is H alpha directly? That would save us quite a bit of trouble. We could get rid of the smoothing, which is actually a fairly complex optimization problem, because if I go back to what it is here, right, it's an optimization problem here that is very high dimensional in general, right? Like this would be a state on the order of n qubits, for example. So it's a fairly complicated problem, whereas alpha is just a real parameter, and we can actually get tighter bounds. So this has been worked on before, in particular the fully classical case, so where A and E are both classical. This has been worked out by Hayashi back in 2010, where he proved this theorem. So if we look at the quantity that we're interested in bounding here, he gives an upper bound of this form here. So the prefactor here changes from 1/2 to alpha minus 1 over alpha. And then we get this H alpha here as we want. And then optimizing over alpha here gives a good error exponent in the IID case. And of course it's fully usable as well in the general case. What happens if we move to the quantum case? So first the CQ case, so the private simplification case, where A is classical and E is quantum. Hayashi also proved a theorem about this, except it does have a few drawbacks here. So first of all, it doesn't use the same definition of Rényi entropy, so it uses the Petz definition rather than the sandwich definition, which is a little bit worse in general, but that's not so bad. The bigger problem, however, is that there's a prefactor here that depends on the number of distinct eigenvalues in one of the operators that arises in the expression. For the IID case, that doesn't matter so much because that scales polynomially in n if we have an n qubit state. So it doesn't matter so much because here the important term is exponential. We have a polynomial prefactor that doesn't matter. However, in the general case, it's not so good. So we don't have any control over this in the general case. Or to have any control, we'd have to go back to smoothing, and then there's not much point to doing this. And he also has a version that involves the ratio between the largest and smallest eigenvalue that basically has the same issue, that it's not so good in the general case. And finally, in the fully quantum case, so in the decoupling case, Sharma has a theorem that looks a lot like Hayashi's CQ theorem. So the bound looks like this. So again, we have the part of it that we want, and again we have this number of distinct eigenvalues here. That has the same drawback. Again, it's good for IID because it's only polynomial, and it's bad in general. And this can be used to get error exponents for lots of IID tasks in quantum information theory. This is all done in this paper, given hence the title, Exponents Galore. Now this talk, what I'm going to talk about today, is a result of this type, but that doesn't have this drawback involving the number of distinct eigenvalues. So the bound looks like this here. So we have the term we want, we have the same prefactor here in the exponent, alpha minus 1 over alpha, and then we have another term here that's basically upper bounded by 2, so this doesn't matter. And now the point is that using this, we can replace the core of the proof that I gave earlier. So in the fully quantum asymptotic equipartition property, so this proof here, we can cut out the H epsilon here and only do this part of the proof, which means it looks like this here. So we want to, in the IID case, we want to lower bound H alpha of A1 to n given E1 to n. In the IID case, it's equal to this, and then we pay the same price we paid earlier, and get something like this here. And now if we optimize this whole expression here over alpha, so this here including the prefactor because alpha is involved in it, we can get an error exponent that's at least this, for example. So we can get this very easily, and it's not so easy to get using the smooth min entropy approach. Another thing we can do with this is to combine the main result with entropy accumulation. So just a very quick summary of what this is. It's a technique for bounding. So the original is for bounding the smooth min entropy of a state that has this structure here, where we start out with a state rho R0e, and we have an n-step process here that generates systems A1 to AN, T1 to Tn. And the way you should think of this is, for example, this would be, let's say, a DIQKD protocol, where at every step here would be one CHSH game. And here, the A systems you should think of as, let's say, Alice's output bit. And T here would be test bits, which you could think of as winning or losing the ith CHSH game. So at the end, you would have a state rho A1 to N, T1 to N, E, and would like to bound, so the original would be bounding this here, 1 to N given E, so getting a lower bound of this, and usually in let's say the IQKD protocols, the lower bound here that you expect would depend on what you observe on the T system, so concretely on the number of CHSH games that you've won. So you observe an event that the Hamming weight of T1 to N is equal to W, and here you would want a bound here that depends on what you've observed here, so on the value of W. So you're going to have a trade-off function here that I'm going to call f of W, which is the amount of Shannon entropy, or von Neumann entropy rather, per round, that is consistent with what you've observed. So that's consistent with the number of games that you've won or lost at CHSH. And this is very useful for proving security of DI protocols. And like I mentioned, so this is the original result, looks like this, right? So it's a lower bound on H min epsilon in terms of the trade-off function. And the core of the proof is very similar to what I showed earlier, right? Which means that it goes through the sandwich Renyi entropy, And using this result, now we can cut off the middleman, because we don't need to lower bound this anymore. We can just lower bound h alpha directly using also the trade-off function. So now we can do the same substitution with the same advantages that we had before. So we're again able to easily get an error exponent for the IQKD protocols. And here's what the result ends up looking like. So we get this fairly simple expression here where the quantity that we'd like to bound here is just upper bounded by something that's 2 to the minus n, and then we have a nice error exponent here that involves the trade-off function here, and this is the rate at which we're trying to extract bits at the output here. So this is the extraction rate that we have, and v is some constant here. And one big difference compared to what happens if we use the original entropy accumulation theorem is that the probability here of seeing a particular event on the test system, so a certain number of CHSH games that were won, enters the expression in a very natural way here. In the original EAT approach, we sort of had to take a guess as to what it was, or at least have an upper bound on what this quantity was, and it entered the bound at the right here. Whereas here it sort of weights the trace distance here in a very natural way, so we don't have to take any guesses as to what it is or really care about it in any way. Now, before I get to the end of the talk, I'd like to say a few words about the proof idea for our main theorem, and basically it's based on norm interpolation. There's something called the Ries-Storin theorem that's about interpolating between two norms. So let's say we have a p norm here, a p theta norm that's somewhere between p0 and p1, and where they're all related by this formula here, where theta is some parameter between 0 and 1. And it's possible to prove that for any f, its p theta norm is less than or equal to this quantity here that involves the p0 norm and the p1 norm. That's it. So we get some kind of interpolation between the p0 norm and the p1 norm. And what we do is use essentially the same idea as in the proof of the Ries-Storin theorem. So it turns out that we can write the Sanush-Renyi entropy as a norm here, so as an alpha norm, so the same alpha that's here. And we can use a similar technique as in the proof of the Ries-Storin theorem to interpolate between two results, basically. So this one here is that's the original Renner result, which is for alpha equals 2 here, and a trivial result here at alpha equals 1. So I wrote it so that we see the similarity between the two here, but here we see that this is just 1/2 here, and this is just 1. So it's really the original Renner theorem, and here this is fairly easy to see that this is actually 0 here, so that this term doesn't exist at all, and this term here is 2 here, and this is trivial because of course for any state the trace distance between two valid states is always going to be upper bounded by 2, and we basically used a norm interpolation technique to interpolate between the original proof of Renner and this trivial result that it's always upper bounded by 2 at the one norm. And in the end, the interpolated result is exactly our main result here. And finally, I'd like to conclude with some open problems. The first one is whether we can also Regnify all of one-shot quantum information theory. And by this I mean essentially doing the same thing I did in this talk, but to problems beyond private simplification and decoupling. Now the fact that this works with decoupling gets us part of the way there, in the sense that decoupling itself can be used to prove all kinds of other results. And so if we take the Renyi version of decoupling that is in this paper, we can get all kinds of other results as well. Now the problem is that approach is going to give us linear combinations of H alpha terms, which are not going to be optimal in general. So for a lot of problems, for example, where we would want, let's say, a Renyi mutual information rather than a difference of Renyi entropies. And so we'd probably need more specialized Renyified theorems beyond those that I talked about in this talk. So I'll leave that as an open problem. And one particular reason to do this is to deal with the so-called simultaneous smoothing problem in multi-user quantum Shannon theory. What happens is that in many quantum Shannon theories involving multiple users, so let's say broadcast channels or multiple access channels, what often happens is that the solution is given in terms of multiple smooth entropy terms. So we have multiple terms involved. And so each of them have their own optimization problems. So we have one state, and then there's an optimal state with an epsilon of it. And if this happens for multiple smooth entropies, the optimal state is going to be different in general for all of these different terms. And sometimes the fact that these are different states causes problems in the whole thing. Like we'd want one state that achieves all of the smoothing problems at once. And one way to deal with this is to just not use smoothing anymore. So if we have a Renyi version of the theorem, then this problem just goes away by itself, because it just disappears and we don't have to worry about it anymore. So that would be one problem that gets sidestepped entirely using this approach. And of course, the other big reason to do this is to be able to get good error exponents of them. So basically, we'd have results like the ones I presented here for all of these other problems in one-shot quantum information theory. And with that, I'd like to conclude by encouraging you to go and read the full paper. Thank you.